Welcome back. So today we're going to talk about isotope notation and isotopes. First, we're going to figure out what the subatomic particles are, what their symbols, and how we can determine things for neutral atoms, and then dive into more isotopes. You've probably heard the term before, you may not know exactly what it is. Anyway, so the first thing we want to talk about is the atomic number, which is given the symbol Z, capital Z. Capital Z, that's referencing an atomic number. And that tells you the number of protons that are in that element. Right, our periodic table is organized by increasing atomic number and whatnot. And we'll talk about the periodic table and its organization a little bit later. And we're talking about neutral atoms. So in a neutral atom, the number of protons and the number of electrons are equal. Okay, that's a neutral. And right, we may have mentioned them before, an ion just happens to be an atom with a charge. And what that means is that the number of protons is not equal to the number of electrons in an ion. So whenever we're talking about a neutral atom, this is true. Protons and electrons are equal in that atom. An ion is just talking about some atom, or in the case of your polyatomic ions, the number of protons and electrons are not equal. So whichever one is present in greater amount determines what the charge is. But for most of the stuff on the worksheet and these examples that we'll be doing here is that we're assuming that these are neutral atoms, so the protons and the number of electrons are equal to each other. Then the next thing we need to discuss is the mass number. So we've got atomic number, which tells you the protons. The number of protons will tell you the number of electrons in a neutral atom. And then the mass number, which has a symbol A, is equal to the number of protons and the number of neutrons added together. You notice the electrons do not show up in this because the electrons, as we mentioned on the prior page, on page 2, when we're filling out the table, is that the relative mass of a proton and neutron are roughly equal. They're not exactly equal, but the proton is like 1/10,000th. It's a tiny, tiny, tiny fraction. So their mass doesn't really contribute anything to the overall. So the mass number is just given as the number of protons and neutrons added together, right? It will be a whole number. Just like the atomic number is a whole number. Both of those are going to be whole numbers because you can't have a fraction of a proton or a fraction of a neutron. Then our AMU is an abbreviation for atomic mass unit. And this is when we're talking about individual atoms. This is the unit that we'll use for mass of individual atoms. And the AMU, the atomic mass unit, is defined as 1/12 the mass of a carbon 12 atom. And just talk about what this represents in a second, because that is the mass number. Whenever you hear something named like carbon 12 or nitrogen 15 or some element followed by a number, this is one way of expressing which mass number of that element you're talking about. And we mentioned protons and neutrons are about 1 atomic mass unit each. And we pretty much just assume the electrons are weightless, even though we know that's not true. They do contribute just a tiny amount. 1/10,000th of compared to a proton and neutron. So unless the presence of like 8 to 10 electrons in an atom are not going to change the mass of that atom by any measurable amount. Now just keep in mind, if you're wondering, if you've had chemistry before, you're wondering about if these are about 1 atomic mass unit but they're not the same as no. Then if you take the mass of a proton and add to it the mass of the electron, you get the mass of a neutron. And so just by knowing that, one, you can make probably the leap to understand that a proton and an electron combine to form neutrons and vice versa. But these two are pretty much have the same mass just because of how small the electron's mass is. So that's why we can get around by saying they have about the mass of about 1 atomic mass unit. Now, going on to talk about isotopes. Isotopes are atoms of the same element, which means they have the same number of protons that have different number of neutrons. Okay, so most elements have more than one isotope. Some have a lot. Some have more than others. How many each have is not something that you can necessarily predict. But there's just some that naturally occur in nature more so than others. But one thing about isotopes is they're just different versions of the same element, meaning they have the same number of protons, but they will have varying number of neutrons in the nucleus. Okay, that's what all an isotope is. So to make it easier to identify which isotope you're talking about, you have to use the mass number, which happens to, if you remember from up here, the mass number is just the number of protons and neutrons that are present in that nucleus. And then if we're writing the name out, just like we did with up here carbon 12, just says after the element's name, you add the mass number. And this number is not found on the periodic table. Okay, so mass number is not on the periodic table. What's on your periodic table, if you take a look at it, is that you've got the atomic number, and then you've got the average atomic mass, which is a topic for the next day's classes. All right? But if we want to do a couple exercises getting familiar with what's the difference between these things, so if we want to figure out in each of these cases what is present, what type of subatomic particles are present. Looks like I'm not finding a ruler handy. So I will use the next best thing. I'll use my binder as a straight edge just to make a quick table. So if I want to find the number of protons, neutrons, electrons in each isotope of potassium, I need to have access to a periodic table. So remember on the periodic table, the atomic number is listed for each element. Right? Potassium symbol is K, not P. P is phosphorus. So if you look on your periodic table for K, you'll see that the atomic number of potassium is 19. So since these are both potassium, they both have 19 protons. Since we're talking about elemental potassium, not some ion of potassium, that means the number of electrons are the same because we're talking about, remember, neutral atoms. So neutral atoms, protons, electrons are equal. Now, these two things added together will make up the mass number. So this is the mass number for both these isotopes, potassium 39 and potassium 40. So you can kind of think this plus this value that we don't know have to add up to 39. So hopefully you can possibly do, this plus this has to equal 39 in this case. So the protons are 19. So 19 plus this is equal to 39. So hopefully you can see, well, there's 20 neutrons present. Likewise, in potassium 40, you've got 21 neutrons present. So that's the difference between potassium 39 and potassium 40. Same number of protons, electrons, just different numbers of the other things. Now, if we want to do the same thing for carbon 13 and carbon 14, draw another, oops, I'll use my phone as a straight edge, because why not? Get there. Oh. Well, those buttons are kind of making things a little bit more less straight. But we do this. If we want to see the difference, the number of subatomic particles present in carbon 13 and carbon 14, you just need to look. Carbon on the periodic table, carbon, right, is like symbol C. And carbon's atomic number is 6. So that tells you that in each isotope of carbon, you get 6 protons, and since we're talking about neutral atoms, the number of electrons are also 6. So carbon 13 means that this number plus the neutrons have to add up to 13. So we've got 7 neutrons in that case and 8 there. The carbon 12 example that we used up here, you can probably understand that this isotope of carbon only has 6 neutrons in the nucleus along with those 6 protons. Now, I want to talk about isotope notation. And it's just a condensed way to, instead of writing out, carbon 12 or phosphorus or potassium 39 or potassium 40, there's a condensed isotope notation that's given this way, where X represents the symbol of the element, and then you put the mass number up top, and then as a superscript in front, and then atomic number is a subscript in the lower left corner. Okay. And sometimes you'll see the atomic number, which is the number down here, not listed. But please get in the habit, for the sake of this class, of just putting the atomic number down here. Because you can get the atomic number if you have a periodic table by just looking at the symbol, finding that on the periodic table, and looking at the atomic number. But we want to get practice writing these appropriately. So if we want to write the isotope notation for the potassium and carbon isotopes mentioned in the previous example, so remember we had potassium 39 and potassium 41. So for the potassium examples, symbol's K. We know the atomic number for both are 19, so that goes down here. And then up here is our potassium 40 and 41. There's our mass number. Whereas the carbon, for the carbon 13 and the carbon 14, this would be the isotope notation for the carbon 13 and the 14 from the prior example. Okay. So here's a little small chart that is similar to the homework that you picked up on that worksheet. And the way that this lists is this column here is giving you the isotope notation, well, the name of the isotope. In this column, you'll put the isotope notation like this with the symbol and the numbers. And then here, you just want to fill in everything else. So in each of these cases, right, these things are giving you as much information as you need to fill in everything else. So for example, nitrogen 15, well, the 15 here tells us the mass number. The name, nitrogen, allows us to look at the periodic table and see that atomic number is 7. And if the atomic number is 7, protons are 7. And since we're talking about a neutral atom here, the protons and electrons are equal to each other. So these 3 columns right here are all going to be the same. Atom, the number of protons, electrons, and the atomic number. Because we're not talking about ions. And lastly, the neutrons is just going to be mass number minus the protons, because these 2 values here add up to the mass number. You can also think about it this way, right? Protons and neutrons equal mass number. So 15 minus 7, this is 8. Then our isotope notation, right, if that's N, 15 goes up here because it's the mass number, the atomic number goes down there. So I would probably ask you to pause the video, try your hand at filling out these blanks, and then when you restart the video, then you can check your answers. So I'm just going to put this So when you're checking your answers, do need your periodic table. And I'll just mention that if you didn't pause the video to go back and try this on your own and just kind of copy down what I have, you're really not getting much out of this, which I know some of you are doing. But again, you know, if you know how to do this and it makes some sense, then maybe you don't have to spend as much time filling this in. And you've got that entire worksheet as well. So hopefully you can check your answers there. If you have any questions to ask about in class. 3 isotopes oxygen listed as oxygen 16, 17, and 18. If we just wanted to write the isotope notation, you know, the symbol for this, right? We've got our oxygen. Mass numbers go up top. And the atomic number for oxygen is 8, so we put that down there. Then we have listed three isotopes of chromium, chromium 50, 52, 53. You just want to figure out how many neutrons are in each isotope. So chromium has atomic number 24. So all you're doing in each case is taking the mass number listed and subtracting 24 from it. So 50 minus 24 is 26. 52 minus 24 is 28. And this one, 53 minus 24 is 29. So that's how you can figure that out. All right, see you in the next one.